Hello everyone and welcome back. In this video we will talk about the relationship between confidence intervals and hypothesis tests. Both confidence intervals and hypothesis tests have the same assumptions and conditions. They are two different perspectives of looking at the same set of data. Confidence intervals start with the sample data and ask what are the plausible values for the population parameter. Whereas for hypothesis tests, they start with a proposed parameter value and ask if the data are consistent with that value. The results for a hypothesis test should be consistent with the corresponding confidence interval. As confidence intervals extend to both sides of the point estimate, they will naturally correspond to two-tailed tests. So for a significance level of alpha in a two-tailed hypothesis test, the confidence level of the corresponding confidence interval is 1 minus alpha. In other words, for two-tailed hypothesis tests, the alpha level plus the confidence level will add up to 1. So for example, for a two-tailed hypothesis test with a significant level of 0.05 or 5%, the corresponding confidence level for the confidence interval will be 1 minus alpha or 1 minus 0.05, which will be 95%. Now if we're working with a one-tailed hypothesis test with a significant level of alpha, then the corresponding confidence level of the confidence interval will be 1 minus 2 times alpha. So for example, if for a one-tailed hypothesis test of an alpha level of 0.05, the corresponding confidence level will be 1 minus 2 times 0.05, which is 90%. Now recall from section 4.1, we calculated a 95% confidence interval for tossing 100 coins, which observed 39 heads, and the confidence interval for the proportion of heads was between 29.4% and 48.6%. Now because 50% did not fall within our interval, we concluded that our coin is not fair. And when we performed a two-tailed hypothesis test with a significance level of 0.05 from section 4.4 with the same set of data, we obtained a p-value of 0.0278, which provided sufficient evidence to conclude that the coin is not fair. And so both of these methods provided us with the same conclusion. Now let's suppose that we had chosen 0.01 for the significance level in the coin toss hypothesis test. Would we have made the same conclusions as for the 0.05 significance level? Well, if the alpha level was 0.01, our p-value, which is 0.0278, is greater than alpha. And if our p-value is larger than alpha, then we would fail to reject the null hypothesis. And recall that the null hypothesis in that test was assuming that the coin is fair, which means that there is insufficient evidence to conclude that the coin is not fair. And so now let's also verify this result by constructing the corresponding confidence interval. So if the alpha level is 0.01, then the confidence level is 1 minus alpha. So 1 minus 0.01, which gives us 0.99, or a 99% confidence level. So what we want to construct is a 99% confidence interval So recall from example 4.1.8, we have a sample proportion, which is 0.39. We calculated a standard error, which was about 0.04877, and the critical value for 99% confidence is 2.575. So now let's construct our confidence interval. So we take our point estimate, which is 0.39. We add and subtract the critical value of 2.575 times the standard error. So we have 0.39 plus or minus a margin of error of 0.12559, and so our confidence interval is from 0.264 and 0.516. And notice that for the 99% confidence interval, our interval contains 0.5, which can suggest that the coin may be fair. So we don't have enough evidence that the coin is not fair. So since our confidence interval contains 0.5, we cannot conclude that the coin is not fair. And this is the same conclusion as the 1% significance level hypothesis test. And this will conclude our lesson for this video. In the next video, we will look at some of the types of errors that we can make when we perform a hypothesis test. And I'll see you then.